Hello everyone. I hope you are all safe so far. So today we will talk about explicit decomposition of a representation. So let's start with a finite group G. Assume that rho 1 up to rho k are the all inequivalent irreducible representations. Of course, we are talking about complex representations, and the dimension of Wi, where Wi is the vector space on which the representation rho I is happening. Then let the dimension of that be Ni, and the character of the representation rho I we denote it by chi I. So all these are given to us. So now for any representation V rho of G, one can define the following operators pi for each I in 1 up to k. And in the class, we have seen that these pi's are projection operators. Let vi denote the image of pi. Then we have the decomposition as v equal to the direct sum of v1 to vk. This is called the canonical decomposition of G. So all these VIs are in particular G invariance of spaces. So this is what we have already seen in the class. So the content of today is the following, that today we will talk about a method for explicitly constructing a decomposition of rho into irreducible subrepresentations. Let me remind you what the decomposition means. By decomposition, we mean that we have to find subspaces, G invariant subspaces, of course, such that the vector space on which the representation is being happened can be written as a direct sum of those G invariant subspaces. Okay, so let's fix the setup for today. So here, as usual, G is a finite group, and these are all irreducible complex representations of G. So the setup is exactly same that we have seen earlier. Now for each I, we fix a basis E1 to En I of Wi, and as soon as we fix a basis, we can write down the matrices of the linear operators. Just a minute. We can write down the matrices of these linear operators, and let's denote the matrices by the yeah. So somehow it is creating a problem. Let me try to fix the view. So view should be fit with. So what I was saying is, so as soon as we fix a basis, you need to E and I. So we write the matrix of rho Gi by this. So my indexing set is alpha beta. So where alpha beta runs from 1 up to Ni. So this I stands for the I that we have fixed. And this is a typical matrix coefficient of rho Ig is with respect to this basis. Okay. Okay. So let's go ahead. So given any representation rho on a complex vector space V, for any pair alpha comma beta where alpha and beta are in 1 up to Ni, we can define the following linear map from V to V. How is this defined? So we will consider the matrix coefficient of rho G inverse, the matrix coefficient of the place beta alpha, and get it with the, I will multiply this by this, the linear operator rho G, and then take the sum and then just scale it. So this is my linear map, which is certainly linear map from V to V. So this is what let me just tell you that. So what are the things to define this PAB? So I need to define PAB, I need, of course, the irreducible representations, And once I fix an I need a basis. Then with respect to that basis, I have to write down the matrix coefficients, and use it with the help of matrix coefficients and the representations we have considered. We consider this PAB. Okay, so this is what we can define for every representation V rho of uh, of G. Okay, so in particular, when this row is for some J from 1 up to K, one row J, then we will see the following, that what happens to E gamma, where gamma is a base, E gamma is a basis element. So when rho is in particular some rho J, we want to know how it acts on a basis element. So it is very easy to see. So we just write it. This is just the definition. And then what we do is we know the matrix representation of the operators rho ij. So the matrix of rho the matrix of rho jg is the following. That's how we have defined. So once once this is the matrix, then rho jg of E gamma is nothing but the so to obtain this, we have to just consider the gamma column of the matrix. Okay, so the gamma column is precisely this. So therefore, in view of this, so this becomes, okay, so this becomes precisely this, because that's how the matrix representation of a linear map helps us. Okay, so so once we know the matrix representation of rho jg, so rho jg of E gamma means we will need to consider elements from the gamma column of the matrix, and using that we have to form the combination. That's what we have done. Okay, these are our elements. Using that we form the combination. Okay. Now we just do some simple interchange of the order of the summation. So we take this one outside and push this inside, and also we push this one by the order of G inside. That gives us this. Okay, so this is nothing but just some manipulation. We pull this here and push this there, and also push one by mod order of G inside that. Now, if you look at the quantity which has been put between the pair of parentheses, so does it remind you something? So this type of objects we have already seen earlier. So if you remember, when we were discussing some important corollaries of Schur's lemma, then we already dealt with such expressions, and we know what are these. So if I and j are not same, that means the matrix coefficients are coming from two mutually non-isomorphic irreducible representations, then this guy has to be 0. Okay, so thus if I not equal to j, so let me just again tell you. So in the particular case when rho was rho j, if this j is different from I, then certainly P alpha beta of E gamma will be 0 for any gamma there, and E gamma is a typical element in the basis. So in that case when I is not equal to j, then P alpha beta as a map from Wj to Wj is a 0 linear map. Clear? So therefore now we will move to the case when I equal to j. So when I equal to j, we also have a expression, we also have a formula to deal with such expressions. So this is precisely this 1 by ni delta beta alpha and delta alpha gamma. Okay, fine. Yeah. So what happens at that time? Okay. Sorry. So there is some small typo. So instead of delta beta alpha, it will be delta beta gamma. Okay, so there's a small, there's a minor mistake. I'm sorry for that, but please take a note of that, that this is not just delta beta alpha, this is delta beta gamma. So in that case, we have P alpha beta of E gamma should be P alpha beta Ni, the summation, and then this quantity will appear here. Okay, fine. Now in view of this, what can we see? So if gamma not equal to beta, so then these are all, we know that the delta beta gamma and delta alpha delta, these are all Kronecker delta notation. So what happens? Suppose gamma not equal to beta, then this guy is again through 0. Okay, and when gamma will be beta, then what will happen then? If gamma will be beta, so this guy then it will be 1. So the rest thing will be precisely this. So only the term corresponding to delta equal to alpha will survive, and that will give us delta E alpha. So summarizing everything, what we find is, so what in the case when I equal to j, P alpha beta acts on the basis elements of Wi in the following way, that it sends E beta to E alpha and sends everything else to 0. Okay, so that's what we have so far seen. Fine. Now you see, so therefore P alpha beta, again let us see, we have just seen P alpha beta sends E beta to E alpha, P alpha beta sends E beta to E alpha, and every other vector 0. So from that it is very easy to see that this summation when I equal to j, so sum of these operators, linear operators, is nothing but identity. Why? It's very easy to see, because suppose if you just apply it on any, let's say E beta, so only the term P beta beta will fix it, and any other summand will push it to 0. So therefore all total, the entire sum will fix the vector E beta. Okay, so once we have that, this is an important observation. Next we will see this. What happens when we compose these two maps, P alpha beta and P gamma delta. Okay, so we claim that this is going to be the following. Why? That's also very easy to see. How to see that? We will apply it on any basis vector E sigma, and now see, suppose I mean the formula that we have already seen, P alpha beta of E gamma is 0 if gamma not equal to beta, and when in the case gamma equal to beta, it will be E alpha. It will be E alpha. So therefore, what we have is the following, that if sigma not equal to delta, then it will be 0, and when sigma equal to delta, then P delta gamma, P gamma delta of E sigma, it will be E gamma. So that also gives us two possibilities, that if gamma equal to beta, then it will be E alpha using just the previous formula, and otherwise it will be 0. So the upshot is the following, that what we get is, once beta gamma equal to beta, then on the image will be E alpha, which is same as the image under this map. Okay, and otherwise it is 0. So that establishes this formula. Okay, is it clear? So I'll just suggest you to check it on your own, that you just apply it on any vector, you just apply it on any basis vector E sigma, then you will see the effect of applying this on E sigma is same as effect of applying this on E sigma. And this is because this is because the following. That's what we are discussing. Okay. Now one more thing we will need. So what happens, suppose we have this P alpha gamma, and then we compose it with the linear map rho ig, then what happens? Okay, So it's again is very easy to see. If gamma not equal to delta, then from our earlier formulas this will be 0. If gamma equal to delta, then this guy will be E delta, E alpha, right? E alpha gamma E delta, so it will be E alpha. Now again, since we know the matrix representation of rho Ig, so once we know the matrix representation, then it should not, then we know how to get this. This will precisely, you have to consider the alpha column on the alpha column of the matrix and then form the combination. So that's what it is. Okay, so these are my matrix coefficients, and using that, if we just if we just form the combination accordingly, we get this. And then we also should recall that what is E beta. You can, E beta is nothing but P beta gamma of E gamma. Okay, so therefore putting all together, what we get is, for every delta, rho Ig composed P alpha gamma of E delta is same as this applied on E delta. Why? Because this is easy to see. If delta is gamma, then this side, so we have just checked that then these two are same. Otherwise, if delta is not gamma, then both the sides are 0. Okay, this is just a simple checking. If delta equal to gamma, that's what we have just checked. And if delta not equal to gamma, then this is also 0. This side is also 0. Okay, and this once, since this holds for every basis element E delta, therefore that means the composition of these two linear maps is basically following. Okay, so again, just let me remind you that let me remind you that this happens. So we can define P alpha beta for any representation rho, and in particular when we consider rho J, then we made this explicit computations, and those computations says that if J not equal to I, then all these linear maps P alpha beta will be 0, and in the case when I equal to J, then we have these formulas. Okay, so this is what we have proved when rho is rho I. Okay, rho is rho I, and in general rho is rho J, where rho J is one of the irreducible representations. And in fact, so this is not just for rho J. So any representation isomorphic to this rho J's, for this, even this will hold, passing through an appropriate isomorphism. Okay, so basically the formulas that we have derived, the formulas are for the representations which are irreducible. So this formula is valid on for any irreducible representations. So when the irreducible representation is isomorphic to rho I, then we have this. Otherwise, if the irreducible representation is not isomorphic to rho I, then this P alpha beta, what we can define is entirely 0. Okay, so with the help of these formulas, in the next video we will see how to get the decomposition of each VIs. So using these formulas, we will see how to arrive at a decomposition of each VI into irreducible subspaces, and each of these irreducible representations will be isomorphic to rho I. We will see that in the next video. Okay.